All right, today this is on linear systems. Linear systems are immensely important in math when we move on after high school. Linear systems, and more generally we talk about solving linear systems, we call it linear algebra. Linear algebra is super important in engineering, it's super important in physics, it comes up all the time. It's not as easy as it sounds. Solving 2 by 2, linear systems with 2 equations and only 2 variables is pretty simple, but it gets more complicated as you get bigger linear systems. And that might even sound strange. How could you have systems of more than 2 variables where it's a linear equation? Well, you can. We can have linear equations with as many, arbitrarily many variables. The graphs of those things just don't look like lines anymore. They look like other things, but we'll talk about that later. Today we're going to focus on small linear systems. We would call them 2 by 2 linear systems, meaning 2 equations with 2 unknowns or 2 variables. So x's and y, our variables would typically be x and y, and we have 2 different equations. Okay, so let's first of all just kind of talk about what it means to be a solution, remind ourselves of that. Remember that a solution of an equation in 2 variables is just an ordered pair that satisfies the equation, which means it makes it true. Would everybody agree that 3, 6, the ordered pair 3, 6 is a solution of the purple equation? If I plug in those x and y values, doesn't it make that a true statement? Yeah. And so does 6, 4, right? Okay. So visually what that looks like is this. Visually it just means that both of those 2 points, oh darn it, both of those 2 points are on the purple line, right? Everybody agree? That's if an ordered pair is a solution of an equation, then it just means that that's a point that sits on the graph of that equation. Give me 1 to 5 on that concept. Does that all make sense to everybody? Okay. All right, so then what happens if we add another line? Now we have a system. A system of equations just means more than 1 equation at the same time. So now I've got a 2 by 2 system, 2 equations in 2 different types of variables or unknowns. Is 3, 6 a solution of the red equation? Thumbs up or down? Yeah, it is. It works. Is 6, 4 a solution of the red equation or the orange equation? No, doesn't work, right? If I plug in 6 for x and 4 for y, the orange equation is false. It's not true. So that is not a solution. So then let me ask you, is the ordered pair 3, 6 a solution of the system of 2 equations? It is. Is 6, 4 a solution of the system? No, it's not. Because to be a solution of the system, you have to be a solution to every equation in the system. And what do you think is going to happen if I graph the purple and the orange lines together? Where are the green and red points going to sit in that system? Where's the green point going to sit?
On both.
Okay, so if it's on both of them, what's that mean?
It's
at the intersection. Yeah, isn't that the only point that's on both lines is the intersection?
Yeah.
Right? So that must be the intersection, and that red point was the solution to the purple equation but not the orange, so it must be some other point on the purple line but not the orange line, right?
Yeah.
Okay, well, let's just verify that. Yeah, that's what we got. Good? Okay. All right. Okay, so there's really only 3 possible ways. If we have a system of 2 equations and 2 variables, there's really only 3 possible types of outcomes. One of them would be the one like we just saw, where we have a single intersection where the 2 lines intersect, right? They cross at one point. Other possibilities would be maybe the lines are parallel and they don't ever intersect, so there's no solution. Or maybe the lines exactly coincide, so they're the same line, in which case there are an infinite number of solutions. Every point on one of the lines is also on the other line, right? Okay, how do we classify these? Well, we use some adjectives to do that. we always say that any linear system is either consistent or inconsistent. Consistent just means it has at least one solution. Inconsistent means it has no solutions. So the first option and the third options would both be consistent, whereas the middle option, the parallel option, is inconsistent. So that's one adjective we use. And then we join that to another adjective. We either say that a system is independent or dependent. Independent equations are equations of different lines. Dependent equations are equations corresponding to the same line. So the first two options would both be independent systems, and the third option would be a dependent system. So if we just combine those, then how could we describe this first one using both adjectives? Well, the first system, where there's only one intersection, would be a consistent independent system. Okay? The second one, where we have parallel lines, would be an inconsistent independent system. And the third case, where we have the same line, well, that would be a consistent dependent system. Make sense? Okay? Okay. So now on to the nitty-gritty here. Let's review, and you guys have done all this stuff, but we're going to maybe go a little bit further with it today. So how do we solve 2x2 linear systems? We have two methods. One method is the substitution method. This is a method that's we can easily use if there's a variable in one of the equations that we can easily isolate. And what are the steps here? I don't really want to focus too much on the steps. We'll just look at some examples, and this will all come back to you. So we're going to solve one of the equations for one of its variables, which really just means, step one is we're just going to isolate a variable in one of the equations. As soon as we do that, we're immediately going to put a box around it because we're coming back to it. That's what we call our substitution equation, and we're coming back to it. That might seem really elementary, but it's important. When you do higher level math problems, like in college when you're solving big linear systems, doing stuff like that is so valuable. It makes it, when you've just got pages and pages of dense algebra, it's really nice to be able to just find the substitution equations because they have a box around them. So that's a good idea in the future, now and in the future. So after we isolate a variable, we're going to substitute that into the other equation for that variable. That's step two. And then what that's always going to give us is a simple equation, linear equation, with only one type of variable that's easy to solve. So we solve for that variable, and then as soon as we solve for one of the variables, we just go right back to the boxed equation and plug it in to solve for the other one. Okay, and then we would check our solution in both of the equations in the system to verify that it's a solution of the system. So let's try this. Okay, so how about this example? We want to isolate one of the variables. Well, that's already done. We've already got two variables isolated because these linear equations are in slope-intercept form. So how about if we just pick the bottom one as our substitution equation and we substitute that into the top equation? Okay, so then what are we going to get when we make that substitution? What's going to be on the left side of the equation? X minus 9. We're swapping that y for an x minus 9. And what's that equal to? Yeah, negative 7x minus 1. And then now that's easy to solve, right? We'll just push the x's to the left, push the variable or the constants to the right, and I'm going to get, what, 8x equals, if I add 9 to both sides, 8x equals 8. So what's x equal? 1. There you go. Okay, so then we solve for one of the variables. Now the next step is we got to go find the other one, right? So step 4, we're going to take this value of x that we found and we're going to plug it into the boxed equation. And what's that give us? So we get y equals our x value, which is 1, minus 9, which is what? Negative 8. Okay, so that gives us the ordered pair x equals 1, y equals negative 8. And I could check that by plugging it into both of my original equations just to verify that it works. Okay, make sense? Okay. How about this one? Isolate y in the bottom equation. How do you identify a variable that's easy to isolate? What kinds of coefficients are you looking for? Yeah, in fact, we want either 1 or -1. That's it, right? We don't want to, if I have a coefficient other than 1 or -1, usually that means if I isolate that variable, I'm going to get fractions in my solution or in my answer, and I don't really want to substitute a bunch of fractions, right? So we only use substitution if it's really easy to isolate a variable, which means it has a coefficient of 1 or -1. That's it. But in this case, we do, right? So that bottom equation, if I isolate that y, what do I get? -7x plus 22. So we put a box around it, and we substitute into the top equation. Okay, so if I substitute into the top equation, what's that going to give me? I'm plugging in 6x. Ah, good. Okay, and I'm going to make that substitution. I'm going to replace the y with that expression. And all that is equal to -28. Okay, so then we just solve this thing, right? If I distribute the -5, what do I get? Plus 35x. What is it? 110 equals -28. I could combine those into what? 41x. Add 110 to this side, and I get $82. Yep. So if I divide each side by 41, what do I get? 2. Yeah, you got it. I get 2. So now what? Yeah, I'm going to plug in up here, which gives us y equals -7 times 2 plus 22. So -14 plus 22, what's that? 8. Okay, and I've got my ordered pair, which I could easily check with Desmo Scientific. Okay, give me 1 to 5. Does that all make sense? Okay, good. All right. How about that guy? Thumbs up or down? Substitution a good idea? Ah, thumbs down, definitely. Real difficult to, I mean, I can isolate a variable, but if I isolate any of those variables, I'm going to get an expression with a bunch of fractions to substitute, and I don't feel like doing that. So we move on to plan B, which is elimination, which frankly is just a better way to do it. Okay, elimination. Why is it a better way? Well, for one reason, because it's more generally the way that we would approach solving larger systems, larger than 2 by 2. So what do we do with elimination? We want to make sure we put all of the equations into, well, I mean, you don't technically have to do this, but this is generally the way we like to do it. We like to write our linear equations in standard form, all the linear equations in standard form, and then we want to add the equations in such a way that we can cancel one of the variables. Okay? So if necessary, we're going to multiply one or both equations by some non-zero number, so that the coefficients of the variables of that, either x or y are opposites. So when I add them up, they cancel. When I add the equations, that will eliminate a variable, hence the name elimination, which gives me an equation with only a single variable after one is eliminated, which I can solve easily, and then I just plug that back into the easiest of the original equations to find the other variable. Okay, so what's that look like? How about this example right here? So with this example, is it really warm in here? Or is it just me? Seems really warm. Yeah, man, it seems really warm. So which variable would be easier to eliminate here, x or y? I could do either one, but I'd always like to multiply by the smallest things possible. X would be, wouldn't it? Now, right now, it's not set up to eliminate an x. If I add those two equations up, I would get 2x plus 6y equals 10. It didn't do me any good. I still have two equations, two variables in that equation. But if I multiply the bottom one by what? Or the top one? -1, yeah. Then it's going to work. Now, does it seem mysterious that we're able to add up these equations? We're going to get to that step and we'll talk about it. So the way I like to show this is I'm going to have a plain arrow if I'm not changing anything. If I'm not distributing anything, I'm just going to rewrite that equation the way it is. So x plus 7y equals 17. The bottom one, you guys correctly told me I should multiply by -1. So I'm going to put a -1 bubble in the middle of that arrow, which means I'm going to distribute -1 to both sides. What does that give me? Okay, good. Now I'm going to add those up. That's called the principle of linear superposition. That says we can take any linear equations and we can always add them. We can always add linear equations to linear equations and get other true linear equations. It's a concept that we use a lot in math and physics, but it's kind of easy to convince yourself of that. When I add these equations, look at that bottom equation. Doesn't that say that -x plus y is equal to 7? They're equal, right? So if I add -x plus y to one side of the equation, that is the same thing as adding 7 to the other side because I'm adding the same thing to both sides. Does that make sense that that should be okay to do? And it is? All right, when we add those up, look what happens here. Something good happens. The x's cancel, and I end up getting a new linear equation, but this time it's only got y's in it. 7y plus y is 8y. 17 plus 7 is 24. So what is y equal to? 3, yeah. We're halfway there. Now what?
Do the same thing for the
Same thing? Well, okay, what do you mean by same thing?
eliminate the y.
I could do that, and it would work. That's just a lot of extra work, though. There's an easier way to get to the other answer. Yeah, I could just take this, because I know the value of one of the variables, I could substitute that into either one of these original equations and solve for the other variable. And that's pretty easy to do. So we're going to do, that's step 5, right? We're going to take y equals 3, and how about the bottom one? That looks a little easier. I'm going to plug it in there. Now, what's that give me if I plug in y equals 3? X minus 3 equals -7. So what does x equal? -4. Okay, and I've got my solution. Okay, give me 1 to 5. Does that all make sense? Okay. Let's try, I'm going to skip that one. Let's just skip up to this guy. What do you think? Which variable is slightly easier to eliminate? And kind of the rule is you just always want to multiply by the smallest numbers possible. Yeah, probably x's. Right? I can multiply by slightly smaller numbers if I get rid of the x's. So what would I do to the top equation?
Multiply by 2.
2. Yeah, now how are you getting that?
Because we need to have the same number of x.
Yeah, good. And you're finding the least common multiple of the coefficients of x, 5 and 2, would be 10, right? So we're just going to get 10s. Good. So we multiply top one by 2, and we get 10x plus 6y equals -14. Bottom one we would multiply by -5. Yeah, good, because we want them to cancel, which gives us -10x minus 14y equals -15. And if I add these up, the x's cancel in this case, and I get 6y minus 14y is what? -8y. Did I do that right? I think I messed something up here. Oh, I didn't, that's supposed to be, I multiplied by 2. What's that supposed to be there? I was supposed to multiply by -5. Yeah, that should have been -35, huh? Okay, so now, (6y minus 35y), what is that, -29y? Equals -29, so what's y? 1. Okay, and then I'll just plug that back in to bottom equation, let's say. And I get 2x plus 7 times 1 equals 3. So 2x equals -4. What's x? -2. Good. So we get the ordered pair, -2, 1. That's going to be the point of intersection of those two lines. Okay? Okay, let's just zip through. These will be quick ones, but I want you to see the outcomes. So on this one, eliminate x's. Seem good? So multiply top one by what? 3. So I get 6x plus 12y equals 114. Multiply bottom one by -2. -6x minus 12y equals -114. Okay, what happens when I subtract? Yeah, what do I get on the left side? 0. Everything cancels. What do I get on the right side? 0. Everything cancels. Okay. What's that mean? Okay, infinite solutions. But I got to be careful. Like, just saying infinite solutions isn't quite good enough. Because even saying all reals isn't quite good enough. Because it's a little more. Can I just randomly pick any value of x and y and expect it to work? I can't. I can't. Because that's, now you're right in recognizing here that this is a true statement and it's always true. So think what the math gods are communicating here. If the variables drop away from our equation, it means they don't matter. The system is insensitive to the values of x and y. Well, you could, or we could just leave it like that if we want to. But my point is, the fact that this is true means there's an infinite number of solutions, but what would the graph look like?
It'd be one line.
They were the same line, okay? Do you see that that's different than saying an infinite number of solutions are all reals, though? Because really what that implies is that all the solutions of either one of those lines work for the other line too. But there's still, we got to be careful because the solutions to like that top equation are still very specific, right? I can't just pick any random values of x and y and expect them to work in that line. The solutions of the top equation are all of the points that satisfy that equation. So it's still, it's not like it's just any values. It's just all the values that work on one line work on the other one also. You see the difference? Okay, why it's a little bit more precise than just saying all reals are infinite. Okay, what about this one? Same kind of thing. Multiply top one, leave top one alone, right? We'll just leave that one alone. Bottom one, multiply by -3. So I get -6x minus 3y equals 15. Add those up, and I get 0 equals 22. What's going on there? No solutions. What's true about those lines? Parallel. Okay. All right, last one. Try that. Go to the boards. Try that one. How are you going to approach that system? What's really ugly about that system? Fractions. Now, can we leave? How are the lines supposed to be written if we're solving using elimination? What form do they need to be in? standard form. So I need to clear all those fractions, don't I? Now, we don't really care though. See, this is where I told you guys, remember, we're going to break these rules. Do we really care if the coefficient of x is negative? No, because it's going to have to end up being negative. One of them has to be negative anyway. So we're going to forget about that rule. We don't really care about the fact that a has to be positive, but we do need to clear the fractions so that we get only integer coefficients for a, b, and c. And then from there, once we get this in standard form with integer coefficients, then we can kind of figure out a way to make something go away. But go to the boards and try that one. Good job. First people all day to get that. That's good. That's good. So what can we do here? So we want to clear fractions right now. You guys were all on the right track. We're going to multiply. We'll distribute 30 through the top equation, which is just going to give us 30 over 6 is 5 times 7 is 35x. 30 over 5 is 6 times negative 9 is minus 54y. And then 30 times negative 2 is negative 60. Good. Okay, we distribute 60 through the bottom, right? Which is going to give us 60 over 12 is 5 times negative 5 is negative 25x. 60 over 10 is 6 times 7 is plus 42y. And then 60 times 1 is 60. So now we've got standard form, both equations. So there's a couple things you could do here. You could look for the least common multiple of 35 and 25, which is 350. I could multiply the top by 10 and the bottom by 14 and make those go away. That's fine. That would work. Okay, that's probably the most direct way. You guys actually stumbled on a pretty good way of doing this. If I add these equations up, and this is tricky. This is what we'd call a row operation in linear algebra. You can always add two linear equations and get another consistent linear equation. Another one that's going to work. That's a true statement. So if I add these up, look what I get. I get 10x plus 12y equals 0. That's nice that it equals 0. Okay? And then I could divide this by 2, both sides by 2, and get 5x plus 6y equals 0. Okay, that's a much easier equation to couple with like this one. I could have done it up here. It would have been fine. Could have just done, again, I could have just done this. Could have multiplied the top by 10 and the bottom by 14. That would have worked. Would have been fine.
Where did 14 come from?
Because 14 times 25 is 350. Okay, because I'm trying to get my least common multiple of those is 350. That's going to give me 350x minus some stuff, and on the bottom I'm going to get negative 350x plus some stuff. So those guys would cancel, right? But look at this. If I take this equation right here and this equation right there, all I've got to do is multiply this bottom one by 5, and I can get the x's to cancel. Everybody see that? So I've got 25x plus 42y equals 60. If I multiply this guy by 5, I get, is that negative on that top one? Yeah, it's supposed to be negative. Multiply this guy by 5, I get 25x plus 30y equals 0. Add those up, those guys cancel. I get 12y equals 60, so y equals 5. Plug that right in there, and I get 5x plus 30 equals 0, and 5x equals negative 30, so x equals negative 6. Shouldn't it have been positive 6? What did I do wrong here? Was that supposed to be a negative? No. 60.
It's supposed to be negative 42y, right? Or no?
Was it?
Wait.
No, what did I did something wrong though, because it should have been, I think, wasn't it, didn't you guys get 6?
The 12 is
The 12
negative.
is supposed to be negative.
Oh, okay, there you go. Yep, it is negative. That's it. Perfect. That's negative, which makes that negative, right? Which makes that negative. Perfect. And so that gives us, yeah, when I plug that back in then, I get 5x minus 30 equals 0, right? So x equals positive 6. Everybody see that? Okay. So those are kind of tricky. I'm going to show you guys something that's not normally like a high school thing to do, but I'm going to show you guys some beginnings of some tricky ways to solve linear systems using matrix approaches, using row operations, which makes this stuff super easy. That's what you'll do in college in much more depth. But not quite yet. We'll get there soon. All right. Good stuff.